Recording has started.
I don't think I will use this.
Okay.
Or, yeah. Okay. And is there? That doesn't work. Like, okay. And if I use that, people see it online, or no, they don't. Okay. Well, that's okay. I'm not showing so many things, I think. Turn it on? Who wants me to turn it on?
Okay.
Hello? Can you hear me? Yeah? Great. I mean, but I'm sitting here.
Okay, it's just gone past 1:30. So what we're going to do now is shift our focus a little bit to the more local universe on star formation, stellar pops, and ISM. And it's my great pleasure to introduce Olivier Byrne, who is going to tell us, give us an overview of the PDRs for All project. So thank you, Olivier.
Thank you, Chris. So, my name is Olivier Bernet. I'm from Toulouse in France at CNRS, and so I'll be speaking on behalf of the PDRs for All ERS team about the importance of radiative feedback from massive stars. So the organizers of the conference asked me to try and make connections with other fields presented at this conference. So I've tried to do that as much as possible. Sometimes it's just suggestions, so I'm very open to discuss these suggestions with you afterwards. Okay, I want to start with a little bit of history because everything started in Baltimore, in fact, in 2017. This is Carl Gordon's backyard, sorry. You know, we had this very nice fire, and we all discussed around this fire pit trying to make pHs. And, you know, at the end of that night, we decided, yeah, we should do an ERS proposal with JWST on the interstellar medium. Okay. Before I go to that and I show you the great results we've had with this ERS program, I want to take a minute and talk about something which is maybe a little bit off topic, but not so much, which is a growing concern in astronomy and that is related to the carbon footprint of research. This group of astronomers for Planet Earth, has gathered, I think, over 1,000 scientists now discussing this topic. And in France, we started a nationwide initiative to address this issue, which we consider to be part of ethics of science. It's called Labo 1.5. You can go to this paper in Nature Reviews Physics, which describes what we've been doing. And so the strategy that we put forward to address this question of the carbon footprint of research is first to do a scientific assessment of the carbon footprint of research. This is the first step. If you want to reduce, you need to assess scientifically in a coherent manner. So we developed this open source tool called JWST 1.5, and we've applied that to 800 research units in France in all fields of science. That's tens of thousands of employees. And from that, you can get a really extremely detailed, that's pretty unique, description of the carbon footprint of research depending on the sources of emission. Okay. What I want to say is that ORA is currently supporting an adaptation of this open source tool to the US. And some institutes, like I think Noir Lab and perhaps the STSCI, are you know, going to try and do that here in the US, and I think it's great, and this should be supported. Of course, reducing the carbon footprint, our personal carbon footprint, is something which is difficult because we are intrinsically tied to the use of fossil fuel through structural through structural ties. And this is just an example of a research we have done where we show that the 3-year publication rate correlates with how much you travel by airplane, okay? You can control that by gender, by age, by discipline. It still works. We have statistical significance. The idea here is not to say that we have to stop everything and that we should stop completely flying. The idea is just to say that I think in the context of climate change, there is currently an opportunity to set a discussion on how we use our carbon footprint or how we use tons of carbon in comparison of the scientific value of what we're trying to do, okay? In my case, I haven't been flying for 5 years and I decided to come to this conference because I thought it was very important that I could be speaking about this early release science project with the people here. So here it is, the PDRs for All Early Release Science program on the JWST. What we're trying to do is to assess the effect of massive stars on their environment. And massive stars emit a very intense UV radiation field. And this UV radiation penetrates inside the interstellar medium in regions that we call photodissociation regions, PDRs. That's a schematic, and so the UV radiation goes like this inside the cloud. It's absorbed by the cloud, and then it heats up the gas, and the gas cools in the infrared. So what you see with James Webb is really the cooling of the gas that's heated by the UV photons of massive stars. And really the key of this PDRs for All project is to assess how the energy is transferred to the gas inside galaxies, looking at these photodissociation regions. So this is the team, that's the PIs. We have a large extended core team and also 122 science collaborators. Our target is the Orion Nebula, and we had 40 hours with 3 instruments on JWST. I want to take a minute to thank all the people at STSCI who helped us implementing this project over the last years. This was really a great help. Okay, so data. This is the NIRCam composite image. This is not the full field of view, it's just a part of it. But you can see how beautiful this is, of course. The trapezium cluster is somewhere over there. So you have the massive stars from the trapezium here on the corner. We left them outside to avoid saturation. And so the UV light goes and reaches this structure here, which we call, because we are very original, we call that the bar. So it's the Orion bar, and that's where the UV light is absorbed by the ISM, okay? You can look at the sort of the details of these NIRCam images, and I don't have time to go to the numerous details that we see in these images. They're related to young stellar objects of many different kinds, outflows, intricate structures. We found a bow wave also around this B star here. And you can go to the paper of Emilia Barr, which is now accepted, and it's available on arXiv. A little bit, additional details about all these protoplanetary disks, so illuminated protoplanetary disks that are present inside the Orion Nebula, and for which we have a wealth of JWST images that complement very well now the Hubble data. Bless you. Okay, so if you go really deep inside the nebula and look at some of the details, you can see all these structures, which at first look like filaments, but now we're pretty convinced that these are not filaments, and that what we're seeing is sort of, like the edges or the illuminated surfaces of some kind of stair structures, and so these, this sort of wavy pattern is probably related to some kind of instabilities related to the radiative feedback on the ISM from the trapezium stars. Again, all details in Emily's paper. The perhaps last thing I want to show regarding imaging is this comparison between the NIRCam and the Hubble image. That's a zoom inside the Orion bar. What is very striking, of course, is that you see a great number of details in the NIRCam image that you do not see at all in the Hubble image, and that's simply because dust is absorbing everything here, so you cannot really peer inside this photodissociation region here. Of course, we have imaging, but what we are really interested in is the spectroscopy. We have spectroscopy with MIRI and NIRSPEC over this cut. It's a mosaic of 9 or a bit more IFUs. And so if you look at how the spectra look like in this field of view, that's what you get with NIRSpec. And you can immediately see that the spectra are extremely rich. Okay? We're almost confusion limited in some cases. There are lines everywhere, and from that, you can do a lot of physics. So I will not go in the details of what physics we can do, because Amik will give a presentation later today where she shows how you can use, for instance, the molecular hydrogen lines present in this spectra to derive the physical properties of the gas here, and what this tells you about how the massive stars heat up the gas in this region. Okay, we also have a MIRI spectroscopy, so that goes all the way up to 28 microns. And what you see here is the aromatic spectrum, okay? All these red bands that you see in the spectrum are due to this family of molecules or some related carbonaceous material with CH and CC bonds. And each one of these vibrations, each one of these bands that you see in the MIRI spectrum are related to some specific vibrational modes inside this family of molecules. You can go to the poster of Ryan Sean also to have a lot more details about the analysis of this PAR feature, as we call them, for pHs. What is really nice is, I mean, again, because of the unique quality of the data, we can go really and zoom in inside the spectrum and look at some details, really fine details and some subbands. And now we can look at, you know, the intimate chemistry of these molecules. In particular, you know, if there are some, if there is deuterium present in those molecules or CHO stretch. So this is also really a new field that is being opened thanks to web spectroscopy. We see a number of lines also in the spectrum. I will not talk about them because Asuncion also today will talk about how we can use, for instance, the sulfur lines. And there is an upcoming paper by Dries van der Put that I want to mention, who is doing a huge effort on trying to characterize all the lines that are present in the MIRI spectroscopy. I want to go back to and make the first connection with the extragalactic world, which exists apparently, as we have seen. And this is, you know, a spectrum of the 3.3 micron aromatic band in external galaxies. So the red one is from the GOLS ERS, so it's a nearby galaxy, VV114, and there is this blue curve here that you see, and that comes from the Z=4 galaxy. And so in this case, the detection is with MIRI, okay? So it's really just to show that these molecules, these PAR molecules, are ubiquitous, and most likely we're going to see them in many galaxies. So what can we do, us from the Milky Way, in trying to support the analysis of those detections? Well, you know, using, for instance, machine learning methods, you can decompose the NIRSpec spectra, and we found that you can extract two templates, one which has a strong 3.3 micron band and a tiny 3.4, and one which has a much stronger 3.4 micron band. What you can do is use a linear combination of these two templates and reproduce the data in the NIRSpec data cube, and you can do a ratio of the contribution of these two templates, and that's what is shown here, okay? And compare this ratio to another ratio, which is the pure rotational line of H2 over the integrated intensity in the aromatic infrared band spectrum. And so the data points are in blue here, okay? And you have this sort of shape. And the orange curve is a model. And this model has to do with how gas is heated by the photoelectric heating effect on pH molecules. And you see that there is a very good match. What I want to point out here is that you can use that as a diagnostic tool. So it's the same diagram here. I just left that's the Orion bar theoretical curve. And overplotted are the points for these galaxies from the GOLS project, and SPT galaxies, Redshift 4 is there. Okay? And what you immediately see is that these points do not fall on the Orion bar curve at all, which is not really a surprise. It just means that the heating efficiency in these galaxies is different with respect to what happens in the Orion nebula. Okay? Perhaps here you have shocks, perhaps related to some merger, that increases the efficiency with which the gas is heated, whereas if you go there, perhaps you have no shocks, and some older stars which are less efficient at heating the gas. So this is just to illustrate how we can provide some tools to help the extragalactic community interpret these kind of observations. Okay, I'll switch to another topic also related to the ERS program, and that is this object, this tiny object here that you see, which is a protoplanetary disk. And I want to also emphasize the fact that if you look at the Hubble image, you sort of see it. It's a little patch here in absorption, but really it starts glowing when you look in the infrared. And that's really the first time we can look at this object in great details. And that's a zoom on the NIRCam image. It's a 3-color image. And so what you see is, the scale, you know, we're at solar system scales here. So that's really fantastic. The disk is there, so that's an edge-on disk. You have a jet here, and this is surrounded by this red emission here is a molecular envelope. Okay, it's warm molecular gas that's surrounding the protoplanetary disk. This is a sketch of the same thing. Sorry, I changed the colors. So the trapezium stars are somewhere over there, and what happens, we think, is that you have UV photons reaching the disk and heating up the disk, and the particles, the gas particles, then can get free of the gravitational potential, and so this launches a flow of material which escapes the disk. So that's what we call a photoevaporation flow. Of course, the key question here is how efficient is this process to remove mass from the protoplanetary disk, and how this can be in competition with planet formation. Okay, how fast? What is the mass loss rate associated to this photoevaporation flow, and how this can perhaps suppress planet formation in this kind of environment? And to do that, you need to get more details, and those details, we get them from the spectroscopy. This is the near-spec spectrum of this protoplanetary disk. It's absolutely amazing. So all these are H2 and H1 lines, so there are hundreds of them. But we also see the OH radical, for instance, CO13CO and CO2 ice, so an extremely rich spectrum. And from that data, you can do a number of things. And for instance, you can use the molecular hydrogen lines and their intensity in particular, so that's the blue points on this diagram, and compare that to models of photodissociation regions. So these guys in Meudon have done a unique work of really pinning down how we can use H2 lines to get the physical conditions. And you see that the model can reproduce the observations quite well, and from that we can derive the density and temperature of the gas in this photoevaporation flow, and from that we can get the mass loss rate. Okay, and we get mass loss rates of this order of magnitude, so that's about up to an Earth mass per year. And so this is a lot, okay? It means that you can really suppress giant planet formation over, a time scale of less than a million years. Basically, you will remove all the material from a protoplanetary disk. So in those environments like the Orion Nebula, the question is then how do you form planets? We also obtained MIRI data, MIRI MRS data for this object, and so that's just a slice in the spectrum in channel 1 or 2, I cannot remember. When we got this spectrum, we had no idea what this was, okay? First, we thought maybe this is fringes, and then at one point, okay, this is not fringes. And so we realized probably it's a molecular carrier. So we went to the molecular databases, and in the databases, we could not find anything that would match this signal. So at one point, we thought, okay, then this is a molecule, but it's not in the databases. It's probably never been seen before. And because it's at around 7 micron, we reached the conclusion that probably it was related to the methyl group, okay, CH3. And discussing with the chemists, they told us CH3 plus is a very good candidate. And so we were pretty convinced that this would probably be CH3 plus. And we said, okay, we'll go ahead and publish the proposal that this is CH3 plus, but we thought we wouldn't be able to have a definitive assignment. But then we talked to the spectroscopists, and they said, oh, wait, we've been working on this methyl cation for 30 years in the laboratory and from the quantum chemical point of view. And so very quickly, they were able to make a model, and you can see that the model is pretty good at reproducing the observation, at least good enough to claim that we had a detection, and so we published the first detection of the methyl cation in outer space very recently. If you have a very good eye, you can see that although the match is good, it's not perfect, and there are some differences. And I thought, okay, it's going to take spectroscopists another maybe 10 years to do new experiments in the lab and get a good model. But no. These guys, led by Brian Changala at Harvard, got together and they cracked it in one week. Okay? And they even made new laboratory measurements during the summer, okay? And all together, they were able to produce this simulation. And I mean, it's amazing how good the match is, okay? It's like, a mirror of the sky on a lake. It's really beautiful. So I want to tell also perhaps the people from the instrument teams here that I talked to spectroscopists, like the hardcore spectroscopists in Cologne, and they told me, this spectrum, you can never record it on Earth. It's impossible. So with MIRI, we were able to record sort of in a serendipitous way the spectrum of the methyl cation that they will probably never be able to record on Earth. And this provides very detailed constraints on the fundamental properties of this species, in particular, the interaction between two vibrational modes which are very close, and so they were able to constrain these really exquisite fine quantum details with a spectrum coming from an astronomical observatory. So I think this is crazy that you can put that kind of constraints with a telescope at L2 on really the finest details of matter. So spectroscopists were really happy about this, us too, of course. So how does this compare? So we have this very strong CH3 plus spectrum in our protoplanetary disk. How does this compare to other protoplanetary disks? I'm making another connection here to the talks that will be given tomorrow. I will not go to all the details. This is a gallery of all the spectra that can be found in the literature. And what you see here is mostly you have neutral molecules, H2O, CO, 12CO, some benzene also, some hydrocarbons, but mostly you have neutral molecules. Not so many radicals, just a little bit of OH here, and no CH3+. Except that I saw a poster yesterday where they see a very tiny sign here of CH3+ in TW Hydra. So these disks are, I forgot to say, are isolated disks. Those are disks where you don't have massive stars around throwing loads of UV photons at those disks. So the chemistry is quite different in most cases, but here you do see something that reminds perhaps of what we've seen in Orion. Okay, but the bottom line really about disks as seen with JWST, these isolated disks, is that the chemistry in those disks is really related to what people call the snow and soot line. And so this has to do with the chemistry at the surface of grains and the ices inside those protoplanetary disks. And what you see with JWST really reflects this surface chemistry happening in the dust grains inside those disks. So what does CH3+, the methyl cation, tells us? Okay, so CH3+ was proposed to be a cornerstone of organic chemistry in space in the 70s. So this was almost 50 years ago. Okay, that's a diagram which shows, it's here at the center in this chemical network. So if you look at this, it's like it's doing everything. But then it was never detected. Okay, for years people have searched it and did not detect it. And so this also led to these alternative routes where you have surface chemistry that I just described in the previous slide. So the detection now sort of revives this methyl cation related chemistry. And what happens, we believe, is that this chemistry is activated by the UV photons, which warm up the molecular hydrogen to a highly vibrationally excited state. And this can overcome some endothermal reaction barriers. And so you can have all this network we start, and we don't know where it can go, okay? We're just starting to see what this chemistry, this organic chemistry can produce, and we don't know what it can do. I'm making another connection here. So this carbon chemistry, it can create hydrocarbons quite efficiently in some cases. And what is interesting is that you just need, hydrogen, carbon, and UV photons to make it work. You don't need dust, you don't need, it's very simple. So this could be useful for high redshift dust formation. And we've seen at this conference that in absorption, people have seen in the extinction curves that you have some hydrocarbon-related material at high redshift. So maybe this could help explain also what happens at high redshift. That's a suggestion. Okay, we have another tracer of the photochemistry, and that is OH. As I've shown, in isolated protoplanetary disk, you see a lot of water. In this disk, we do not see any signs of water. Instead, we see the OH radical, and we believe that this is because H2O is photodissociated by UV photons, and the OH radical is left in a highly excited state. And so this is why we see this really high-level energy pure rotational line in the MIRI MRS spectrum. So another sign that not only carbon chemistry, but also the oxygen chemistry is really governed by what the UV photons are doing. And so this is sort of the summary of our findings related to the protoplanetary disk. And so you have to remember that stars form in clusters. So even the low-mass stars form in clusters. Most of them are formed in clusters. And so in those clusters, you will, in all cases, almost have massive stars. So at the moment when you form these low-mass stars, probably nearby you will have some massive stars, and they will throw UV photons at all the early steps of evolution. Okay, this is what is illustrated here. For what concerns this phase, which I've been discussing here, the protoplanetary disk phase, the UV photons hit the disk and they warm it up, and this creates a photoevaporation flow which removes mass very efficiently. And so this will clearly affect planet formation. And the chemistry is also modified by this UV radiation. And so this is important when we are trying to understand the composition of exoplanets. This may affect what is delivered in the end to exoplanet to some extent. And of course, this happens in a few million years, and the massive stars, after a few million years, they're gone. And so what you're left with here is this planetary system, and the massive star is gone. But in most cases, these massive stars will have existed. And in fact, in the solar system, we know that there were one or several massive stars at the moment the solar system was born. We see that in the cosmochemical analysis from the radio isotopes. And so this, this UV irradiation scheme is probably relevant also for the early solar system. And so more generally, I think what I want to say and insist on here is that we need to take into account the role of UV in planet formation physics and chemistry. Okay, and so this is my last slide. Of course, this is to be continued. And so this is a list, a non-exhaustive list of early papers. Some of them are in preparation, accepted or published. You can go to the PDRs for All webpage. We'll be updating these links very frequently. And that's it. Thank you.
Thanks, Olivier. That's fantastic. So we're doing something a bit different. We have a virtual moderator for this session. So I'm going to check in with Naomi first to see if there's any questions online, and then we'll go to the room. So
I haven't got any questions online yet.
Okay, cool. Thank you, Naomi. So I think it was you first, and then you, and then we'll...
Hi, Naman Bajaj, University of Arizona. You said that this disk winds are probably being driven by external photoevaporation. I just wanted to ask, have you considered internal photoevaporation as well, since there is a jet, so there's probably an accretion shock and then photons from there?
Yeah, usually you can have, of course, photoevaporation driven by the internal star. This also works. Usually, however, this is much less efficient than what we observe here in terms of the mass loss rate. We have very large mass loss rate. It's really hard to explain with internal photoevaporation. And also, when you just make the orders of magnitudes in terms of the intensity of the UV field, it's really, for all the outer disk, it's really much larger than what you get from the internal star.
Time for one more. And can you grab the mic while you're doing this one? another roaming mic now.
Hi, Kieran Rogers, Leiden University. I also have a question about the photo evaporation. So those mass loss rates, I think, are insanely high. And you're talking about the impact on planet formation, but that's going to affect the final mass of the star as well, right? Are you looking into how this is fundamentally changing the final mass the star gets to and the impact on the IMF in these kind of regions?
Yeah. I mean, that's a consequence of these findings, I think, and some people are looking at that with models, and I've been looking at that with models for a while, population synthesis models. I don't know if there are works related to the mass of the stars themselves, but for the planets, yes. And what is shown really is that if you have, everything depends on the initial mass of the star. For solar mass stars, this effect will not be very efficient because the gravitational field is larger, but for M stars, you will efficiently remove a lot of mass. And in fact, this may explain why in the exoplanet community, you don't see any gas giants around M stars. I think people, and I'm happy to discuss that with you here, but people usually say, okay, these low mass stars, they're low mass, so they don't have gas giants, but you know, what is the physical explanation behind is not so clear.
Hi, Olivier. Great talk. I just wanted to ask you a question about the non-detection of the free micron absorption feature in the protoplanetary disk. Because I saw in your paper, there is a statement about the fact that even the James Webb resolution might not be enough. And so this is intriguing to me. So I just wanted, to ask you about that.
Yeah, so that's really a pity because it's really a trick of physics. But the cross, because these things are seen in fluorescence, they're extremely bright in emission. But the intrinsic cross section of the 3.3 micron band is not so high. Here, what you see is just all the UV that is converted to IR, so it's very bright. But the cross section itself is not very high, and so it's very hard to see these things in absorption because usually it's blended with many things, and again, the cross-section is not very large.
We have to move on, sorry, Ryan. So if we can thank Olivier again. Next up, we have Carl Gordon, who will telling us about interstellar dust extinction from JWST, and we're all set. All yours, Carl.
Thank you. Thanks for to the committee for allowing me this opportunity to talk about one of my favorite subjects. I like dust. So I'm going to be talking about interstellar dust for JWST. Maybe. There we go. So I like extinction because unlike what we just heard about, it's a direct measurement of the dust grain abundances, size, composition, and shape without the messiness of excitation. And it gives us clues, and the clues of this are in the continuum and the features that we see. And the other reason I like it is because as I get more senior in the field, see, I'm using the right word now, I like straightforward measurements. And in the end, these are just ratios of either a star versus a model or a star to a star. Simple is good. I'm going to focus on near and mid-infrared spectroscopic measurements and the diffuse ISM, talk about pre-JWST results, as well as some clues, some hints of what we're seeing with JWST. The teams make the dream work. Really it does, not just for JWST, but for all these projects. I'm just putting all the names up there. You can look at them later if you really want. So I'm going to start off in the mid-infrared with Spitzer. And so the goal here was to understand what the diffuse ISM extinction curve looks like at spectroscopic resolution. You may be surprised to hear that we didn't really know what the diffuse ISM looked like in detail. This is a sample that was picked to have UV extinction curves as well as the ability to measure them with Spitzer. So you see the UV on the left. There's a couple of sightlines in there that are dense, and I'm not going to talk about those. Those are the ones that look different. They don't have the nice 2175 angstrom bump. And then you can see all the extinction curves, and what you can maybe see is it's fairly flat in the mid-infrared, and there's a strong feature at 10 microns, and there's even one at 20. These are the silicate features. These have been known, but they're very strong, and they dominate the mid-infrared. If you do an average, you can see there that the UV looks really normal. That's one nice thing about having the UV. We can test it versus our larger sample of UV extinction curves, and this one looks indistinguishable. And now we also can make the mid-infrared extinction curve average. You can actually see that, you might be used to thinking about extinction always going down as you go to longer wavelengths. That's not true. As you can see, once you get past about 6 microns, you go into the silicate features and they dominate the extinction beyond where JWST can observe. There's the 10 and 20 micron features. They're pretty easily modeled with an analytic function. You can then look at the residuals and you don't see any other features. But wait for JWST. What we found is the diffuse ISM extinction curve is lower than most of the literature work. That makes sense. A lot of the literature work on Spitzer and so on was mixing both dense and diffuse sight lines. We're just doing diffuse sight lines, so we're actually biased towards the smallest dust grains. So we're expecting to be lower in the mid-infrared. If you have bigger dust grains, you should be higher. And that's actually what we see. Now, that was the mid-infrared from 5 to 30 microns with Spitzer. Now, what about the near-infrared? Again, prior to the work of Marjorie Declure, as a postdoc working with me, we only used photometry really for the mid-infrared extinction curve. So we set out to try to do it with spectroscopy. Now, prior to JWST, the best you could do was from the ground, especially at above 2 microns where Hubble doesn't take spectra. So doing this with NASA's IRTF SPECS instrument on Mauna Kea, as you can see, there is lots of atmospheric absorption. That's why we love JWST. But we did the best we could at the time, and here's a bunch of extinction curves. There's 1 or 2 that might have a feature at 3 microns. Those are the dense sight lines that have ice. We're not talking about those today. And you can see in general, this one is fairly smooth. There are no big features. In fact, if I go to the next slide, you can see on the right that a power law works really well for the near-infrared wavelength range. We don't really see any other features that are significant until we get to JWST, of course. And again, this was a sample that had UV extinction curves, so we can make the UV average, and it looks normal. So we really are probing true diffuse ISM with these measurements. All right, now let's put it all together. This is the most recent thing I've worked on. So now this is putting it all together. Now for the first time, we can do a spectroscopic extinction curve from the far UV at 912 angstroms all the way up to 30 microns. We haven't been able to do that prior to this. A range of RVs. RVs are this AV over EB minus V, this total to selective extinction, and it's a rough measure of grain size. So higher RVs means larger grains. And as I said, this is the first time it's all spectroscopic. Those are the 4 papers, samples that it's based on, so we can span this wide wavelength range. This is what you should be using now for JWST. And it's in this dust extinction AstroPi affiliated package. You can install it and run it now. We also provide all the previous ones if you somehow prefer something not as good. Okay, so how do you make one of these things? The RV-dependent relationship is really simple. I told you I like simple. This was found in 1989 by Cardelli, Clayton, and Mathis, this RV dependence, that in fact if you plot, it's RV versus A lambda over V, well it's really 1 over RV versus A lambda over AV, it's a line. And it's a line at all wavelengths. And I show you a few select wavelengths over there. You fit it. There are things that deviate. It's not perfect. The deviations are real. What we're describing here with this relationship is the average as a function of RV, not every extinction curve. So if you do that and you set it up well, and you fit this at every wavelength, and yes, there's a lot of wavelengths fit there, you can plot the intercept on the top and then the slope. And the nice thing about the way this was set up, and I give Ed Fitzpatrick the credit in 2019 to set it up this way, is the intercept is actually the average at RV of 3.1. And so now you can see, oh, that looks like a normal RV of 3.1 to me. I'm used to looking at these things. Notice there's a strong feature, the carbonaceous feature at 2175, and there's also strong features at 10 and 20 microns in the silicates. And then you can look at the slope, and this is telling you how extinction varies with dust grain size. So the 2175 angstrom feature varies with size. It's due to small grains. That makes sense from a theoretical point of view. Notice the silicate feature isn't there anymore. That's because it doesn't vary with size, and that is how we understand how the silicate feature works. It is from all dust grains. It is a little different from previous stuff. From previous work, not surprisingly, we have, we're more recent, we have more data, we are spectroscopic now. All the previous work was based on photometry at some wavelengths and spectroscopy at other. And not only that, as you can see, that the previous work didn't extend out fully to include the full JWST wavelength range. So now to JWST. We have 21 sight lines and 2 cycle 1 programs. And this is what you should be using soon for both understanding dust grains and maybe you like to correct for dust extinction. Who would want to do that? So there are two programs. One's MEAD. It's a Cycle 1 program led by Marjorie Declure. 9 sight lines with a range of AVs that are 1.2 to 2.5, not very large, but a nice range of RVs and a range of molecular hydrogen fractions. So we can understand something about how dust extinction varies. The other thing, neat thing about this sample is it has pre-existing, there's a pre-existing HST program to get atomic dust abundances using gas phase measurements and depletions. That'll be very exciting. We have good existing photometry. This is just like the next program. We use MIRI-MRS spectroscopy and NIRCam GRISM spectroscopy to cover the kind of interesting ranges that we like for interstellar dust, which starts at about 2.5 microns and goes outward. We've got all our GRISM data. We just got most of our MIRI-MRS data, so this is very fresh for MEAD. Whiskey is the other one. You can see the theme on the names here. Sascha Ziegers leads this one. There are 12 sight lines. Now these are for much higher AVs, so we're probing much more dust. And there's a follow-up HST program to get the optical and UV extinction curves, at least for some of the sight lines, for as many of the sight lines as we could. This is very similar, MIRI-MRS and NIRCam GRISM. All the NIRCam GRISM data is taken, and just like the other one, we're still getting the MIRI-MRS data. So here's the spectroscopy where they've been merged. The NIRCam and MIRI data have been merged. For our sight lines, this is a standard way you might see stars displayed if you think in the near and mid-infrared. It's the Rayleigh genes normalized, i.e. take your F nu and multiply it by lambda squared, and that huge Rayleigh genes tail from stars goes away, and you kind of can get them flat, and you can see what's going on. Very clearly, we have very nice silicate absorption. So let's look at that. So this is the silicate absorption. Here I've just normalized it with a line, very simple for both whiskey and mead. And you can actually see I put up a bunch of dust grain models. That's all the solid colored lines, and then the new empirical relationship, G23, is also plotted. And you can see the more modern, the more recent dust grain models do a better job of actually matching the silicate feature in both its center and width than some of the older ones. We now have good measurements, and now the dust grain models are doing better at fitting the data. As you can see, that's a little stronger for the whiskey sample and weaker for the mead, as expected, given they have different amounts of dust column. Now, what about the smaller features, which you may have just seen whopping in emission in the PDRs for all Orion bar? They're not whopping in emission. Now we have an absorption. So now we're going to be able to measure the column densities of the atoms that are in these molecular bonds. And the thing that I've been learning is how to actually interpret these features. Well, they're really telling us something about this CC bond. That's what that feature tells us. It doesn't tell us much more. And this is the strongest feature in absorption we see outside of the silicate. We also see, well, the next strongest feature is actually the CO. That was not expected. This is not CO like gas phase CO. This is carbonyl. It's attached. So what I think is happening, and what we're discussing now, is it means that the carbonaceous grains have been oxidized. And maybe there's some other features, but now we're getting weak, and we're going to need more than a couple of weeks to do our analysis to find out what's really there and what's not. Now, we also have 3.4 micron and 3.3, which is very exciting because this is where in the models you can actually see there's the 3.3, that's aromatic, that's aliphatic. Except these are what our spectra look like, and you can see there's these very nice wave functions in them, which are not real. And so we're waiting on the needed calibration observations will be taken in about a year, and that's just the way it happened. But fortunately, as I said, I like simple things, and so if you do the simple thing and divide the two samples, one has more dust than the other. One has AV of 5, one has AV of 1.5. You divide out all the calibration issues that go away, and now we have a spectrum that looks much more like what we thought for interstellar dust. We see the 3.4 micron feature, which is stronger in absorption than in emission, and the 3.3 is very weak there. This is really new, just a few days old, and so very excited that things are looking good, that we will be able to do this. Near-term goals for both programs is really to understand the silicate dust, which we have the 10 micron feature. The profile tells us a lot about a mineralogy, the grain size, and shape. The carbonaceous dust, we're going to be able to learn things about different kinds of carbonaceous dust, aliphatic versus aromatic, and the hydrogenation from the CH stretching. Features. Some more long-term goals are to measure the full UV to mid-infrared extinction curve. We'll study the behavior of these features and compare them between different wavelengths. And we'll update the RV-dependent relationship to be even better because it'll have these weaker features in them. We also want to determine the diffuse ISM carbonaceous to silicate ratio directly from the mid-infrared spectra, not indirectly through gas phase depletions in the UV. We also want to compare the features to dust abundances directly. That's one of the strengths of Mead. Whiskey is comparing features with lab data. I really constrain what are dust grains. And then, of course, that'll all help to constrain dust grain models that we then use for a lot of physical stuff. And here is the summary. We have now the first spectroscopic extinction from the far UV to the mid-infrared. It's one relationship for all wavelengths. There you go. You can use this now, install it, run it. If you don't like Python, I can give you 0.1 RV ASCII files if that's what you want. And there are some people in the room who've asked for those, I know. With JWST, we're refining this. This is Whiskey and Mead, and we'll update the empirical extinction models and the dust grain models. And thank you very much.
Thanks, Carl. Naomi, is there any questions online before we move to the room?
Nope, nothing here.
Right. So into the room we go.
So, Carl, 3.4 versus 3.3, what is your interpretation then? Why do you get that ratio and not what we see in emission?
Well, I think the key thing is, and this goes back to my simple thing, in absorption, it's easier to interpret these features because they're directly related to the column of material you have between you and the star and their intrinsic strength. Whereas if you do them in emission, now they have to do with the excitation conditions in addition. So how you excite that, is it through, is it a molecular excitation? Is it more solid state? Is it a luminescence? There's other ways of doing the excitation, and so that'll change the ratios. It's easier to interpret absorption than emission always.
Carl, for all what we extragalactic people care, your advocated extinction curves are not all that different from, say, like Calzetti's, from far UV to, say, like optical. Am I right?
Yes, because I'm talking about extinction, not attenuation. Right? So if you want to get into the question of what happens when you're not looking at an individual point source where the dust is far from it, but you're looking at something like on the bottom, much more complex for a galaxy, now you have rate of transfer effects. Now you have geometry effects that matter. And there are two of them, scattering into the line of sight. So extinction is absorption and scattering out of the line of sight. Now when you have attenuation, you have that, plus you have enough, you can actually scatter into the line of sight. Rate of transfer models, if you do a piece of a galaxy, it's a third of the light is scattered into your beam. And not only that, the different stars are embedded to different depths, and your measurement is fluctuated. So the least attenuated stars dominate your signal. And so this is just makes it's just like absorption versus emission, extinction versus attenuation. Attenuation is harder to interpret. And so, and it's the rate of transfer models, we expect there to be differences like what we see with the Calzetti relationship, which is grayer than the extinction that you would put into the model. It's exactly what we expect from rate of transfer effects. We have models. Many other people have models.
Okay. If there's any other final quick questions? I don't think so. Can we thank Carl again, and we'll move on. Next up, we've got Amit Sidhu, who is, we heard a trailer of this. It's H2 in the Orion bar from Olivier's talk, and Amit is going to be presenting remotely. You can share your screen. We should be all set, Amit.
Can you see my screen?
Yeah, that looks good. And then, right, you're all set. So.
Thank you. So my name is Amit Sidhu, and I am a postdoc at Western University in Canada, working with Professor Els Peters and Jan Kami. First, I would like to thank the organizers of this meeting for the opportunity to let me speak and present some of the work that we've been doing with the data that we observed with the PDRs for all ERS program. So today I'll be presenting to you the results, the observations and analysis of the molecular hydrogen as observed in the Orion bar. So molecular hydrogen is one of the most abundant molecules in the universe. It has a rich rotational, vibrational, and electronic energy states. So figure on the right-hand side shows the energy level diagram of the H2 in the ground electronic state. So for each vibrational energy level, there are a large number of rotational energy states. And the relative population of H2 in these energy states depend upon the number of molecular processes, such as collisions, photoexcitation, and formation. These molecular processes in turn depend upon the gas state, for example, the density, gas temperature, radiation field strength, etc. So by studying the H2 emission line spectra, we can now study the manner in which these energy levels are populated, that is, study their excitation mechanisms, which can tell us a great deal of information about the interstellar medium. So the object of our study is the Orion bar, as Olivier has already mentioned. So you might have seen this image in Olivier's talk already, but just to recap, the ionizing source is on the top right. It has created an H2 region, and then there you can clearly see in this image an ionization front that separates the ionized from the atomic gas, and on the bottom left, we have the molecular cloud. And the next image that I'll show you is the emission that is an image that captures the H2 emission in the Orion Nebula. So this is an NIRCam image that captures the H200S9 line. And now you can clearly see the dissociation front. The dissociation front separates the atomic from the molecular gas, and it runs roughly parallel to the ionization front. The dissociation front, you can see, is highly structured with spatially resolved ridges that you can see. We've also observed the spectroscopic data with NIRSpec and MIDI, and in this image I'm just showing the footprint of the field of view of the MIDI and the NIRSpec. Our field of view captures the H2 region, atomic, and the molecular region. So while we analyze the entire maps, we've also identified some key regions, for example, where we have obtained the template spectra. For example, this is the one region, H2 region, the atomic PDR, few of the proplyds, and in this image here, the green here is showing the H2 emission, and you can we have identified 3 dissociation fronts, the dissociation front 3 being the most brightest. So we have 3 dissociation fronts, dissociation front 3, 2, and 1. With the data that we observed with the MIDI and NIRSpec, we observed a forest of row vibrational lines, H2 row vibrational lines. So this image here is a spectrum, just the NIRSpec spectrum in one of the template spectrum, which is the dissociation front 3. And on the purple here are the positions where we have identified or observed the H2 row vibrational lines. So in our spectrum, we observed 100 of H2 lines originating from V equals to 0 up till V equals to 6 energy states. And we have also observed pure rotational lines from higher J levels, for example, up till J equals to 19 in V equals to 0, 1, and 2 states. This is the first time when we are observing the lines in the pure rotational lines in such higher J levels. We've also constructed the spatial maps of the H2 line. So here I'm showing you 3 maps of the some of the strong lines, the 00S1, S9, and 120S1 line. And we can see that while the H2 emission is observed throughout the map, but the strongest is in the bottom left, which is the molecular PDR. And in that molecular region, the strongest emission is coming from the dissociation fronts. So the contours on these maps are for the 00S1 line, and they very nicely delineate the dissociation fronts. What you also notice is that there is a subtle difference in the spatial distribution of the H2 line. So if you focus here on these 2 dissociation fronts, dissociation front 3 and 2, you would notice that there is a shift in the intensity peak of the intensities of these lines. So in S1, it peaks in the center, whereas in the S9, the peak now is shifted. It's towards the ionizing source. And same, you can see there is a subtle difference in the spatial distribution of 1 to 0 S1 line. The other thing that I want to mention here is that the emission that we see in the atomic and the H2 region, that emission is coming from, it's weak, and it's coming from the background PDR, which is in the background molecular cloud OMC1, and it's not coming from the Orion Nebula itself. But to study the differences in the spatial distribution of H2 a little bit more, we identified this line cut, which is sort of going through the centers of these dissociation fronts, and studied the flux distribution of the few of the H2 lines. So the figure on the right is just the flux distribution of 3 H2 lines, is 00S1, S3, and S9 along this cut. So x-axis is showing the distance from the ionizing source, and it's just the normalized to the flux of the peak flux in the dissociation front 3. So what we're seeing here now is that for each of the dissociation fronts, the 1, 2, and 3, there is a shift in the intensity of the peak position of these lines. The higher J lines, which are shown here in red, they peak closer to the ionizing source, versus lower J lines, such as S1, which is shown in blue, they peak little farther away from the ionizing source. This gives a little bit of an insight into the excitation mechanism of these lines, because the higher J lines, they require much larger energy to excite, and so they peak closer to the star, versus lower J lines, which require relatively less energy and they peak farther away from the star. But the more classical way of studying the excitation diagram, studying the excitation mechanisms of H2 or H2 emission in general, is to construct the population diagrams. So here I'm showing a population diagram for dissociation front 3. So the population diagram are the diagrams where we plot the upper state energy level of a transition on the x-axis and the upper state column density, normalized upper state column density on the y-axis. So in this one, I'm showing the population diagram for V equals to 0 pure rotational line. So on the top left, we have J equals to 1 line, and on the bottom, we have J equals to 19. These population diagrams can reveal a great deal of information about the excitation mechanism. So if it's a straight line, the lines are collisionally excited. The relative population of a level drops significantly, and it can be explained by a straight line. And in our case, we see that J equals to 1 to J equals to 7, the lower J lines, they are collisionally excited, whereas the higher J levels, which require much higher energies, they cannot be collisionally excited. And the dominant mechanism there is the fluorescent excitation, where the H2 molecule, it absorbs the FUV photon and then gets electronically excited and then dissipates its energy by emitting in these higher J levels. Now, these population diagrams can tell us information about the conditions in the gas. So, for example, from collisional excitation, we can derive gas temperatures, etc. So we fit these population diagrams with, we have this nice curves, we fit these with 2 straight lines and get some information about the gas, get some information about the physical conditions in the gas. We fit these using the PDR toolbox. So it's a photo dissociation region toolbox created by Mark Pound and Mark Wilfire. This is a Python toolkit which is used to analyze the observations in the PDRs. So we fit the population diagram with 2 straight lines here. The slope of a straight line, the slope of this line is telling us the information about the temperature, and the intercept gives an estimate on the column density. So with the first few J levels are fit with a colder component, so which are representative of the gas temperature. And so for this one case here, we get a gas temperature of around 600 kelvins, and the hotter temperature, which are in the green, they're given estimate of the excitation temperature, and it's a quite higher excitation temperature of 3000 Kelvin. We can also fit the ortho to para ratio for these lines using the PDR toolbox. And in this case, we're getting an ortho to para ratio of 3, which is somewhat expected in local thermodynamic equilibriums. Since we have the maps we have the H2 emission throughout the mosaic, so we use that to construct the maps of the gas temperature, column density, and ortho to para ratio for the entire mosaic. So we use the first few J levels, which are collisionally excited, and fit them with single temperature to get an estimate of the gas temperature, column density, and ortho to para ratio, which I show here. So the temperature map is on the left, and you can see that roughly throughout the mosaic, the temperature is about 600 kelvins, with a small deviations in the proplate where you have a high temperature or around the dissociation front 1. But overall, the temperature is around 600 Kelvin. We can also derive maps of column density, and we can see that the column density, it probes really well the H2 emission. The contours again here are for the 00S1 line, and you can see that the column density map is following really well the contour of the 00S1 line. And it ranges from 10 to the 20 to 10 to the 21 centimeter inverse square. And we've also obtained the map of ortho to para ratio, which throughout is consistently 3, again telling us that the system is in the LTE.
Dynamic, if that's okay.
So this is so we can also compare our observations with the models. So this is just a preliminary results where we're presenting a theoretical population diagram derived for radiation field strength of 5 times 10 to the 4 and a gas density of 3 times 10 to the 5. We have with these conditions we can obtain the temperatures of around 600 kelvins and produce the column density of 10 to the 20. So this is just a preliminary result. We will be doing a detailed comparison with the Meudon PDR code to get a maps of the gas density and the radiation field strength from these population diagrams. And as I said, this is just a continuing work. Along with the detailed comparison with the code, we will also be doing the analysis of the combined population diagram. So we have observed around hundreds of row vibrational lines from which we have constructed these combined population diagrams. We have the lines in the various ladders, and we will utilize these lines to understand the excitation mechanism of how the collisions are modifying how the collisions are modifying the level population of the higher J lines in these higher levels. So this is also something that we will do with the detailed comparison with the theoretical models. And with this, I'll end my presentation, and thank you all for your attention.
Thanks, Amik. That was great. So time for a couple of quick questions, if there's any online, Naomi?
No, none online still.
And any in the room here? Right, 2 in the room at least, so here first. And then
Hi, Kieran Rogers, Leiden University. I was wondering if you had any ideas about why you have 3 of these dissociation fronts. Like, what physical mechanism causes there to be 3? Because there's only 1 ionization front. So yeah, do you have any ideas on this?
So the dissociation fronts are what I'm calling the dissociation fronts are basically the ridges that we see in the region that's separating the ionization, the atomic region from the molecular region, we're just studying the few of the stronger ridges here. The reason why there are ridges is probably because of compression of a gas, but that's something still being investigated. And I'm not there are more, but we're in our field of view. There are just 3 that we're studying in detail.
Hello, Liz Tarantino from Space Telescope. Beautiful work. I have a question on the column densities that you calculated and whether or not the column densities derived through these H2 lines are similar to column densities derived from, say, the CO or other methods to get at the H2 column density.
So we have not yet done the comparison with the 8 column densities that we derive from the other tracers. So this is still an ongoing work. There are a bit of issues with the flux calibration, and sometimes the column densities can vary if we include more of the lines and some other H2 lines. So this is something which we're still investigating.
Thanks, Amit. Can we thank Amit again and we'll move on? Our next speaker is Asuncion Fuente, who will tell us the third part of the PDR's full trilogy. I think about the sulfur abundances. I think we're driving the slides for this. Is that right, Thomas? So,
yes.
Yeah. Right. So bear with me.
Oh, it is not.
No. Right.
I think
the other version in here. It's okay.
Yes, this is a version with PPT only,
Yeah.
not PPTX. That is the good one.
Yep. Does that look better?
Okay.
Yeah. Okay. So
Yes,
just ask me to move them on, and we can work through this.
okay. Thanks a lot for your help. Hello, everybody. This is the last talk based on the PDRs for all dataset. Olivier has already did an excellent overview of the whole project and also present very striking results. And the same for Amit. In this talk, I want to show you how we are using the PDRs for all dataset to address one of the most important problems of astrochemistry. Next slide, please. And the problem is that we really don't know what fraction of sulfur is in volatiles and refractories in the interstellar medium. We know that we can explain the observation in diffuse clouds assuming undepleted sulfur. This means that all the sulfur is in gas phase. We can, but when we go to molecular clouds, to the cold cores, we need to assume a sulfur depletion of a factor of 10 or even higher, a factor of 100, to explain our observation. And one order of magnitude is a very large uncertainty. And to know what fraction of sulfur is in volatiles and refractory is not important only for astrochemistry or for people that is interested in the interstellar medium. It's also important for people interested in planet formation, because we need to know the fraction of sulfur in volatiles and refractories in protoplanetary disks if we want to predict the chemical composition of the planets and their atmospheres. Next slide, please. So this is Amit already showed this slide. This is the region in which we have complete imaging in the near infrared and the mid infrared, and we have selected several positions that represent different physical conditions in the Orion molecular cloud: the H2 region, the atomic PDR, and dissociation from 1, 2, and 3. Next, please. We have next slide, please. Well, in each of these pixels, we have a spectroscopy information. We have lines of several atoms, ions, and some molecules. And now I have to big a word of thank you for the PDRs for all data reduction team that made an excellent work. From all these lines, there are three that are very interesting for this project. One is the line of S3 plus that is located at 10.5 microns. The other one is the line of S2 plus located at 19 microns. But the most important line is the line of atomic sulfur that is located at 25 microns. And this line is very important because thus far, before the JWST, this line has been detected in very few objects. Our goal is to use these three lines to determine the amount of sulfur in the ionized gas and in the molecular gas in the ion bar. Next slide. Next, please. Okay, on the right you see the spatial distribution of the sulfur lines together with the spatial distribution of the H2 lines that Amit has already presented. As expected, the ionized lines are more intense close to the H2 region. If you look at the image of the atomic sulfur line that is in the top right corner, it's a very noisy map with some instrumental artifact, but what is clear is that the peak, the emission peak, is located in the dissociation front 3, that is the one located farthest from the H2 region. Something also important to comment in this slide is that although the intensity of the ions lines is higher close to the H2 region, we detect the lines in all the region, and the intensity contrast is about a factor of 4. That is not a lot, and this means that the emission from these ionized lines are not coming only from the M42 nebula, but also from the foreground ionized gas that is located between the molecular cloud and us, and that we refer to it usually as the ion bay. Next slide. Next, please. So a few years ago, Rubin and collaborators already calculated the sulfur abundance in the ion bay based on the Spitzer data, and they came to the conclusion that sulfur is depleted a factor of 2 in the gas phase. This means that half of the total sulfur budget is in gas phase in this ionized phase. Next slide, please. We have also repeated these calculations, in this case using the JWST data, and we came to the same conclusion. Our data are in full agreement with those of Rubin and collaborators, and we found a sulfur depletion of a factor of 2 in most positions. The sulfur abundance seems a bit higher in close to the H2 region, but the difference is within the uncertainty. So we have now a good estimate of the sulfur in the ionized part, and now we go to the molecular part that is the most innovative. Next slide, please. And well, to estimate the sulfur abundance in the molecular part, we base on the intensity of the atomic sulfur line. You see on the left, you see the location of the squares we have used to obtain the spectra in the panel, and on the right you see a 3D vision of the Orion bar in order to understand better the situation. We have only one very nice and very intense detection of sulfur atomic line in DF3, and this is the dissociation front that we are going to model using the MEDON PDR code in order to estimate the sulfur abundance. Next slide. Here I want to stress the large effort of the team, because the MEDON team has been working to upgrade the chemistry of this code in order to have the best predictions. And on the left, you see the code predictions for the abundances of the most abundant sulfur and carbon species. The ionized sulfur splash is drawn in the black with a black line, and you see that at a visual extinction of about 2.5 from the abundance of atomic sulfur becomes comparable to the abundance of ionized sulfur. It's interesting to note that at this position, at this extinction, all the gas is in the molecular form and most of the carbon is in CO. For this reason, in our model, we have assumed, we have used the parameters that were fitted using the CO lines observed by Herschel. Next slide. So this is what we know about the abundant salts, but if we want to compare with observations, we need also to study the excitation of the atomic sulfur. The excitation of the atomic sulfur line is collisional, and the main excitation mechanism is collisions with H2. Unfortunately, these collisions were unknown when we started this project, but in our team, part of our team, in particular, Paige Jan and James Buff, have calculated them in a very short time in order to be able to carry out accurate calculation. Next slide. With this upgraded model, upgraded in the chemistry and also in the excitation, we run several models. Next, please. First, we explore the impact of different parameters in the intensity of the atomic sulfur line. We change density in a first place, and of course the intensity of the sulfur line is very dependent on the density, because the critical density of this line is very high, is close to 10 to the 5th. Next, please. In a second place, we explore the behavior with the UV field, and we need high UV fields, more than 10 to the 3, to have large intensities of the atomic sulfur lines, because this line is also very high in temperature. Next, please. Finally, we use the reference model, the model that fits, that provides a good fit for the CO lines, and compare the prediction of this model with our observations. And the good news is that we really have a quite good agreement. We are able to predict the intensity of the atomic sulfur lines within a factor of 2. But at this point, I have to remind you that in the code, in the model, we have assumed that sulfur is undepleted. And this means that we are able to explain the observations of sulfur without assuming any depletion. Next slide. So summarizing, we have now this puzzle. We have calculated the sulfur abundance in different phases in the ionized gas, also in the molecular gas, and we can explain all the observations in the Orion bar, just assuming that sulfur is undepleted or very low depleted, at most a factor of 2. And this is an important result for astrochemistry, because this means that in the regions where we have a high UV field, the sulfur remains undepleted. Next, please. Well, in this slide is just a summary of my conclusions. And also, one word more to say is that the observation of atomic sulfur that now is possible thanks to the JWST sensitivity opens a new tool to understand the sulfur chemistry in the interstellar medium, and to understand also how sulfur is incorporated to planets. I stop here.
So, final check-in online. If there's any questions, Naomi? Oh.
Nope, nothing.
And if not, if there's some in the room. Any takers? If not, can we thank Asuncion again? Thank you for joining us remotely.
Okay, thank you.
So between us and coffee, there's a poster session So this is in the same format as the previous ones. So what we have here, each person will have 2 minutes, and this is in the same format where we have the kind of the lineup here of the next three. I think I first saw this at one of the meetings here many years ago, so I've become immersed in the baseball story here now in the US. So, you know, you've got at bat, on deck, and then I think I want to be careful of the next phrase. What's the next one? Like you're kind of on the bench, right, or in the hole, and then you each know kind of where you're coming through. So I'm going to do a timer, and so when the bell rings, I will cut you off because we're trying to get to coffee. But without further ado. Andrew,
am I using this or one of the mics? Am I using this? Or?
If you want to use this one, it's probably better for the
All right, awesome. So, hi everyone, my name is Andrew Battisti. I'm a research fellow at the Australian National University. My poster is on constraining the link between the 2175 angstrom feature, which is also known as the UV bump, which Carl was talking about before, and polycyclic aromatic hydrocarbons, which are small dust grains seen in the mid-infrared and are postulated as a potential carrier for this UV bump. So the motivation for this is that dust attenuation corrections are one of the largest sources of uncertainty in driving accurate galaxy properties. And this project focused specifically on understanding when the 2175 angstrom feature, which is very prominent, is needed in, needs to be included in those attenuation curves. So to do that, I used the FANGS, JWST FANGS survey and combined it with SWIFT data, which is available for most of those galaxies, to link the UV feature to the mid-infrared PA features. The data were resampled to match the SWIFT data, which I should just mention the SWIFT has 3 UV filters that are nicely situated right on and off the bump, so you can get it very nicely, but you have to normalize it with respect to the total amount of reddening, which we get using the MUSE data that's also available for these galaxies. So that's what's shown here, for example, in this first panel here. The second one is showing PA map for this particular galaxy that I show, NGC 4321, but the trends I'm showing here for this one galaxy are what we see in general across most of the galaxies, so it's representative of what we're finding. The first panel here is illustrating that we find a moderate correlation between the UV bump strength and the PA abundance, but this doesn't necessarily indicate that there's a direct link. It just could indicate that the small grain responsible for the bump is co-spatial with where the PAs are, which are also small dust grains. Perhaps more interestingly is that both of these parameters, the UV bump and the PA strength, anti-correlate with the star formation rate surface density, indicating that these small grains are being easily destroyed by ionizing photons. And so the surface density of star formation seems to be a really good indicator of the strength of the feature. And so it could be like a parameter to use to characterize the strength of it in attenuation curves. If you're interested to learn more, please come and have a chat with me. Thank you.
fantastic timing. So, Liz, all yours.
Hello, everyone. I'm Elizabeth Tarantino. I also go by Liz, and I'm a postdoc in the ISM group at the Space Telescope Science Institute. And today I'm going to briefly tell you about a mystery that's been ongoing for about 30 years now that JWST has solved, the case of the missing pause, and specifically what happens at with pause when you go down to low metallicities. So we've already heard a little bit about pause, but just to briefly describe them, they're these small carbonaceous dust grains in the interstellar medium, and they make these bright, broad, mid-infrared features that JWST is really, really good at observing. So JWST has just been a machine for making these PA maps in the local universe. So PAs are really useful because they are a potential star formation rate tracer, and they're just really, really bright in normal high metallicity star forming galaxies. However, when you go down to low metallicities, the PA abundance is significantly suppressed. If you go less than 20% solar metallicity, about that of the SMC, they essentially completely disappear. So we were trying to investigate why that was happening and if we could possibly find PAs in a low metallicity galaxy. We targeted Sextans A, one of the closest low metallicity galaxies at 7% solar metallicity, and just integrated for over 30 hours on the brightest star-forming region that contains dust. And the really awesome thing is when you integrate that long with JWST, we ended up actually finding PAs. So on the right here, you can see an SED with the PA spectrum in the back. That's just to guide the eye. We only have photometry. And each one of those filters is a filter that we have from JWST. The PA filters are in the colored bands, and you can see that they all have an excess around their bracketing continuum filters. This shows a strong indication that there are PAs present in sextans A, which is a pretty big result because it wasn't sure that they could even exist at these low metallicities. However, these PAs are very different from their high metallicity counterparts. Instead of tracing out the beautiful spiral arms that you see in other nearby galaxies, these are incredibly faint and compact. They're about the size of an arcsecond, which corresponds to about 10 parsecs. Because sextants, oh, am I out of time? If you have more questions, please talk to me.
Hi, I'm Jimena Rodriguez, postdoc at the University of Arizona, and in this poster, I'm presenting the detection of embedded star cluster in the 19 Func JWST galaxies. We started the identification of embedded cluster in NGC 7496, and we found there that the 3.3 micron PA emission works well to detect embedded star cluster. We also found that the number of clusters younger than 2 million years could be increased by a factor of 2 if we added these new detections. Then we will observe spectral energy distribution. We use 5 HTT band, 4 NIRCam band, and 4 MIRI bands, and we found a very distinctive shape, different from the spectral energy distribution observed in older invisible clusters. So we are using these special features that we observed there to expand the detection in the other 18 galaxies. So if you want to know more about this, please search me in the coffee break. I would love to talk more about this. Thank you.
Hi everyone, I'm a postdoc from I'm Jessica Urkel, by the way. I'm a postdoc from the Institute for Astronomy at the University of Hawaii. This is my work as part of the ERS Ice Age team, which uses, or the ERS Ice Age program, which uses a combination of NIRCam, NIRSpec, and MIRI data to observe the chemical composition and chemical evolution of ices in the Chameleon-1 star-forming cloud. So to do this, we look at the ice absorption features through spectra of our background objects behind the cloud. And to do this, we need good photometry of the objects in the background to understand, what they're like. But aperture photometry doesn't really quite cut it, so we use PSF photometry to account for complex backgrounds, crowding, overlapping sources, and skipping a bunch of detail because I know everyone wants to get to coffee. But we do PSF photometry, it works great, and then that allows us to do a bunch of further analysis, including photospheric line removal, extinction mapping, ice mapping. A lot of this analysis is still in progress as well, but on your right, my left right now, is an initial look at the ice map. And the good news is that there's ice everywhere. So there's a lot of H2O, CO, CO2, and other species that are labeled in a bunch of different colors, even in the densest part of the cloud. But the bad news is there is ice everywhere, including from background galaxies where we have ice features on top of the galaxy spectra. So that's making our analysis and even the visualization quite complicated. So if anyone wants to talk about photometry techniques or how to visualize that, that would be very helpful, and I'd be happy to chat. Thanks.
Hi everyone, my name is Max Newman. I'm a graduate student at Rutgers University. I'm going to give you a very quick overview of this work on calibrating the tip of the red giant branch method as a precision distance indicator in the near-infrared wavelengths. Most of this is work with an HST program that was designed as a preparatory program for calibrating the TRGB in JWST. We have 4 fields of view. Well, before I get to that, The TRGB is well characterized at optical wavelengths, so I-band equivalent F814W filter and HST. There is a modest color dependence, which traces the metallicity of the stars in a color magnitude diagram. When you move to the near infrared, however, the TRGB gets roughly 1 to 2 magnitudes brighter, which means you can go out much further in distance, maybe 50 megaparsecs, we have to see. But you have to characterize this metallicity dependence, this color dependence, in order to remove it and standardize the TRGB in these infrared wavelengths. So we have developed a method using HST infrared data to be able to do this. This panel over here, so figures 2 and 3, show the slope characterization at the tip of the red giant branch and the 0 point. And then finally, we have the precision of the calibration. It's a really precise calibration, which is great. And now we're applying this method to TRGB data. We're going to do it in hopefully 22 filter combinations from shortwave, with near cam, and then eventually nearest. If you have any questions about how we calibrate this or what this is going to look like for JWST, I'm happy to talk about it. Thank you.
Hi, everyone. I'm Alec Hirschauer. I'm a postdoc here at Space Telescope. I'm presenting a poster on behalf of my team of GTO observations for program 1233 of Wiki 18. This is the archetypal blue compact dwarf galaxy. It is highly star-forming. It is extremely metal poor at about 3% solar, and it's fairly nearby at 18 megaparsecs. This makes it a really ideal accessible analog for the kinds of systems that we expect were ubiquitous at cosmic noon, the epoch of peak star formation. And so this program, which was PI'd by Margaret Meixner, employed 4 filters each in MIRI and NIRCam, which was based on earlier predictive work for determining the populations of dusty stellar populations. And in particular, we're interested in characterizing stars on the asymptotic giant branch. This is the final short-lived evolutionary phase of low to intermediate mass main sequence progenitors, and they're believed to be a primary contributor of dust. And so in the early universe, however, there hasn't been sufficient time for substantial quantities of dust to be produced. And so we have to ask this question: how does dust production work at very low metallicity environments? And so here we see a NIRCam 3-color image of Wiki 18. You can see highlighting the star formation, recent star formation, and the gas structure. This is an example of some point source detections. And so some ongoing work that's been going on spearheaded mostly by Giacomo Bordolini in Stockholm and Nicholas Cruzet at Leiden, has been able to confirm the presence of both a young and an old stellar population by using extremely metal poor isochrones. And also, with color magnitude diagram analyses, we're starting to isolate the AGB star populations and those of YSOs, which trace recent massive star formation. Ongoing work will incorporate mid-infrared MIRI data to help complement the near-infrared NIRCam data. And what this is going to do is create a larger wavelength baseline to help with identifications of stellar populations and inform spectral energy distribution fitting. So my poster here is available in the Nearby Galaxy Slack channel. Come find me at the coffee break. Thank you very much.
Next up is Christian online.
Yes, I am.
Yeah, great, go for it.
Awesome. Hello, everyone. My name is Christian Boersma from NASA Ames Research Center, and I'm a co-PI on GEO program 1591. Team members include Luel Mandola and Alexandros Margoudakis, who are, like me, both attending remotely. Our program observed 7 extended, well-known, well-studied past sources along the low-mass stellar life cycle using NearSpec IFU. Our program is looking to detect, quantify, and relate any spectral signatures from deuterated pars, par nitriles, and par anharmonicity in the 1 to 5 micron region. There is an enormous amount of extremely rich data. The poster presents a first look using spectra extracted from 1.5 arcsecond radius-sized circular apertures centered on each field of view. In-depth spectral spatial analysis of all features and targets is underway. The spectra show a wealth of features, including the 3.3 micron par complex, a par continuum, and a plethora of atomic and molecular emission lines. In addition, absorption from CO2 ice and water ice can be seen. With a focus on the spectrum of the bright PDR position in M17, the poster presents the results for some feature analysis that helps constrain the astrophysical and astrochemical environment. A paper reporting on this work has just been resubmitted for publication to the Astrophysical Journal. Please reach out on Slack or via email for any follow-ups. Thank you very much.
Thank you. So, hi everyone, I'm Guillaume Vigoureux from the École Normale Supérieure in Paris. So our goal was to try to do a statistical analysis of the pH emission in the Pleiades. So you have on the bottom left a mosaic made by NIRCam near of Merope in the Pleiades. So in order to be able to do a statistical analysis of the pH, we had to remove all the bright sources. So the first step was to remove the 3 big spikes due to Merope. So you have an example on the top in the middle. So this has been done by using many polynomial estimation. So this is quite precise because you can see some complex sources which are appearing and which were hidden by the spikes before. Afterwards, we had to recreate the EPSF of this filter, and it was mainly done by tweaking an algorithm made by Jay Anderson in order to have a better estimation of the spikes. And finally, we use a multi-scale median sigma clipping estimation, which is partly based on background 2D from ProTutils, in order to have to be able to make some in-painting of the remaining compact sources. And with all those methods, we were able to create this map that you can see on the top right of the diffuse emission in this region of the Pleiades. And this map allows us to have 2 main results. The first result is the fact that this angular anisotropy that you can see on the large scale is still there up to super small scales. So this can be understood as the fact that the pH are still coupled with the magnetic field up to those scales. And the second main result is the fact that there is a changement in the regime of the pH around their main free path, which is probably due to the decoupling between the gas and the pH. So thank you for listening. If you have any questions, I will be pleased to answer them later on.
All right, hi everybody, my name is Logan Jones. I'm a postdoc here at Space Telescope, and I am interested in the material and the processes that go into forming new stars and stellar feedback at the scales of 5 to 10 parsecs. And so to learn more about that, my collaborators and I have been using a series of 4 pointings with MIRI MRS towards the center of M83. This is a nearby, very starbursty galaxy, very metal rich in the center, like 2 to 3 times solar metallicity in the center. And so the spaxel by spaxel analysis of like the molecular and ionized gas in these spectra are still ongoing, but we've already had one paper out kind of looking at the high level results from this program in Hernandez et al. 2023. Basically, if we add together all the spaxels in each of these 4 regions to make these 4 kind of mega spectra, and then use this model from Togi and Smith to try to figure out the H2 gas mass from the H2 rotational lines, in each of these 4 kind of chunky regions here, we're getting something of order 10 to the 7 solar masses worth of molecular gas, which that's already extraordinarily high. But what is even crazier to me is that it's actually higher than what you would infer just from the CO observations. So even in the metal-rich core of M83, we're getting anywhere between 30 and 70% CO dark molecular gas, which may have pretty interesting implications for how star formation happens even in these metal-rich starbursting environments. So please come find me, talk with me some more about this. I'd love to hear more about from the PDRs for All folks in particular. Thanks.
Close out. All yours.
Thank you. Last one, I promise. Thanks for sticking around. But my name is Joshua Peltonen. I'm a PhD student at the University of Alberta. And this poster is here to present this MIRI data we have in the local group galaxy M33. There's actually another half of this data set in NIRCam that Adam Smersina is going to talk about in the next session. But with MIRI, not only can you make a beautiful image, but you can also identify young stellar objects. And this is pretty cool because before JWST, the farthest known YSOs were in the LMC and or the SMC as well. And this is over 16 times further away than that, so it's pretty cool we can do that with JWST now. And with these YSOs, we can do some pretty cool star formation science. So one thing we can do, which is in the very bottom right there, is compare the number of YSOs versus mass of the star-forming region, the molecular cloud that they're in. And you can see there's a very similar relation between our molecular clouds in M33 and Milky Way molecular clouds, which is a relation that hasn't been seen extragalactically before, at least I don't think. Another slightly controversial result that we found was looking at YSOs across the spiral arm. And when we compare the amount of YSOs across the spiral arm compared to molecular gas, we find that there's actually an increase in the efficiency that these YSOs are forming as you move across the spiral arm, which a lot of simulations haven't been seeing, and a lot of other tracers that don't look at the as-embedded phases YSOs also haven't seen. So if you want to talk about this anymore, feel free to come chat with me or hit me up on Slack. Thank you very much.
Thank you. That ends this session. Can you just ask you that you're back in 20 minutes for a quick break, because if you've seen on Slack at 5 o'clock, there will be some social drinks through in the cafe and beyond on the terrace. So you can wrap up there.
Recording has